Right. Here's another example. You carry out a reaction mixing 150 ml of solution A and 50 ml of solution B. I'm just using fictitious reactants here, A and B. Carry it out in a styrofoam cup. Your styrofoam cup approximates a calorimeter. Temperature dropped by 0.95. If the heat of reaction is known to be 0.8, calculate the calorimeter constant. Okay, so this illustrates how you can determine a calorimeter constant. You carry out a reaction with a known heat of reaction, then the only unknown there would be your calorimeter constant. Let's illustrate that. Let's calculate that. What is our Q of reaction? It's known to be, for this, 0.800 kilojoules, right? And what is our delta T? Temperature dropped by 0.95 degrees Celsius or 0.95 Kelvin. So delta T is what? Positive or negative? It drops, so negative 0.95 Kelvin. What is the heat capacity of our reaction mixture then? What's the formula? The most important formula to know for measurements of heat for reaction, Q reaction is minus C delta T, right? So C equals Q reaction over negative Q reaction over delta T. Okay? So what is this going to be? Negative of 0.800 kilojoules over negative 0.95 Kelvin. Okay? So what would that be? Okay, let's see. 0.8, and let me change that to joules. So 800 divided by 0.95. 842. Okay. So that's going to be positive 842 joules per Kelvin. Okay, how many sig figs should I have here? Only 2, right? 2 sig figs here. But I'm going to keep that extra digit because I'm going to use this further. Because that's not what I'm looking for. What am I looking for? The calorimeter constant. This is equal to what? The calorimeter constant plus C of the contents, right? So if I only knew what the C of the contents are, I should be able to figure out the calorimeter constant. Do I know the C of the contents? Can I estimate that given the fact that these are aqueous solutions? We can just say that's the heat capacity of the water, right? Assuming it's dilute solutions. Usually that's what we do. So we're going to say then the heat capacity of our contents is equal to, how much water do we have? If I were to mix 150 ml of an aqueous solution with 50 ml of an aqueous solution, what's the total volume essentially? 200, right? So 200 ml, and we're just going to say it's all water, pretty much all water. We're dealing with dilute solutions. What's the density of water? 1.00 gram per ml. What's the specific heat of water? 4.18 joules per Kelvin per gram. Gram cancels out. So heat capacity of contents is how much? (836 joules per Kelvin). So what do we know now? C is C cal plus C contents. How do I solve for C cal? Calorimeter constant is equal to C minus C contents. So it's 842 joules per Kelvin plus sig fig, 2 sig figs here, right? Minus C contents minus 836 joules per Kelvin. So it's 842 minus 836. 6 joules per kilogram. Essentially, for practical purposes, that's essentially 0 within your sig fig limits, right? But if you're going to use it for further calculations, usually when you determine calorimeter constant, you're going to have to, you're using it, you're determining it so you can use it for another experiment. So you can keep it at 6, okay? Keep that extra digit, and you can use that for your further calculation. Okay. Typically, if you did this in the lab, in a freshman chemistry lab using a styrofoam, you're going to get calorimeter constants ranging from something like maybe 25 to 75 joules per Kelvin. That would be the typical numbers you would get. Okay. So how do you determine calorimeter constant? Carry out a reaction with a known heat of reaction. You know your heat of reaction, so you can figure out the calorimeter constant. Then you go around, turn around, use the same calorimeter. Now you know its calorimeter constant. You can use that calorimeter to determine the heat of reaction for another reaction, an unknown reaction. So this process of determining the calorimeter constant is called standardization or calibration.